and welcome back to the LigoLearn Introduction to Functional Programming course. In this module, we will dig in and learn a lot more about Haskell's type system and algebraic data types. Let's get going. We will begin the module by covering some theory related to Cartesian products and then quickly see that theory in practice with tuples and later with other product types. We'll also explore type synonyms and data type renamings, and then we will take a pit stop and have an aside about type classes, something which we will cover properly in a later module. The final part of the module will be where we define our own custom product and sum types, culminating in our understanding of what an algebraic data type actually is and how we can use them. Before we start looking at product types in Haskell, let's cover some theory. In mathematics, there is a concept known as a Cartesian product. The Cartesian product of two sets is defined as the set consisting of all of the possible combination of values. Let's look at an example to illustrate this. Suppose we have two sets, A, which contains the values 1, 2 and 3, and B, which also contains the values 1, 2 and 3. We can create a table to enumerate all possible combinations of values for both sets. Here, the first column contains all possible values of the set A in red, and the first row contains all possible values of the set B in green, and the rest of the table shows all possible combinations of values. So the Cartesian product of the two sets would be equal to the set which contains all of these values, which I have shown here. Now suppose we declare a variable x which has the type of a two-tuple, with the first and second elements both being ints. The value of x could be any possible combination of an int with an int. We can enumerate all of the possible values in a table, just like before. The triple dots represent all of the missing values until either the minimum bound or maximum bound for an int. So what we have here is a product type. It is called a product type because the set of possible values which it can take is defined by the Cartesian product of the possible values for each type. Tuples are inbuilt product types within Haskell, which we have seen before, with their own special syntax of being defined within brackets, with each type in the type signature or each value in the value definition separated by a comma. Here's a question for you. How can we represent a date in Haskell? Well, one of the ways in which we could do it is to create a value of a three-tuple of ints, like so. As you will see, this is not a good way, but it is a way nonetheless. Here we have created a date with the three constituent parts being made up of ints. There are many problems with using a tuple like this. Firstly, there is no way of knowing from the type of int that it is supposed to represent a date. This is just any triplet of ints. Secondly, there is no way of knowing from the type which field is supposed to represent the day or month or year, unless you have some documentation somewhere which states, for example, that the first int is the day, the second is the month, and the last is the year. Then there is no way for someone to know that. And even if you have that documentation, it could just as easily be missed, and people can use it wrong. Also, since everything is an int, there is no way to prevent invalid values being used, such as negative numbers for the day or month. All of these problems and limitations help explain why it makes sense to define our own types to describe our data, rather than relying solely on the inbuilt types. We'll use this idea of a date type as a running example to explain a number of concepts which relate to types in this module. Let's move on. Let's look at a tool which is available to us in Haskell, known as type synonyms. A synonym of a word is another word which has the same meaning, and a type synonym is just like that. It is another name for a type. We've actually already seen a type synonym before. This is how the string type is declared. We use the type keyword, then the name we would like to give the type synonym, and then there is an equal sign and the type we would like the synonym to refer to. Don't misunderstand the type keyword here. We are not creating a new type. All we are doing is creating a new type synonym. We can read the declaration as we are creating a type synonym called string, which is a synonym for a list of char. We can refer to the synonym or the original type in a type signature. For example, in these two code blocks, we are referring to the original type of list of char here and the synonym here. And since they both mean the same thing, the values are constructed in exactly the same way too. Now let's look at how we could possibly use type signatures to represent a date more clearly. Remember, we saw earlier how we could use a triplet of ints to represent the parts of a date, but we said that the type signature does not really tell us enough about which parameter is supposed to be the day, month, or year. So we can create type synonyms, like so, for the day, month, and year, and then use them directly in our type signature. Since each type is actually just an int, nothing changes under the hood, and you can create values just like you would for an int. You could even take this further and declare a type synonym using other type synonyms, like here. Here we are creating a type synonym for a 3-tuple called date, where the first element is of type day, the second is of type month, and the third is of type year. But remember, each of these are just synonyms themselves, so it is really just a wrapper over a 3-tuple of ints. The good thing here is that the signature becomes clearer. We can see immediately that we want the value to be a date. This is much better than having raw ints because it conveys the message to the reader of what the type actually means. Type synonyms can be useful if they improve readability, but since they are actually only wrappers over the underlying type, they do not necessarily mean an increase in type safety. Take for example this date. Since each type is actually only an int, it is perfectly valid for a user to construct an instance of a date like this. But we all know it doesn't actually make sense. The second field is supposed to be the month, but we know there is no 31st month. The situation of putting in an incorrect date like this is perfectly possible in international teams, which have different ways in which they represent the date. A better way of having a date would be to create our own custom type, which validates the input so only correct dates can be created. Type synonyms can sometimes be useful, and it is important to be aware of them. But to avoid the problems we have discussed, we usually prefer to create our own custom types which restrict values to only be valid ones. Let's quickly recap what we have covered with type synonyms before. We know that one way in which we can represent a date is as a 3-tuple, and in order to make it clear which part of the tuple corresponds to the day, month, and year, we've created these type synonyms. And we can use those type synonyms in our type signatures to create more readable dates. Whilst this does indeed aid readability, the underlying type is always an int, and as such, it is still possible to get confused and give values that result in an invalid date, like so. Fortunately, there are better alternatives which can be used depending on the situation. One of these is known as datatype renaming. Datatype renamings are another kind of synonym which offer better type safety. It is great in the situation when we may have a type which can be used perfectly to represent something, but in order to aid readability and increase type safety, we would like it to be called something else. In order to declare a datatype renaming, we write a Newtype declaration. A Newtype declaration creates a new type which has the same representation as an existing type, but which has a separate identity in the type system. Let's have a look at some examples. Here we have 3 Newtype declarations, one for day, one for month, and one for year. You can see that they begin with the keyword Newtype, followed by the name of the type we want to create, and then the equal sign. After the equal sign, there is what is known as a constructor. These are what we need to use to create values of the type. The constructor takes a single argument. In this case, for each of the types, the argument is always an int. How would we create an instance of a 3-tuple representing a date now? In this case, we need to call the constructors to create the relevant instances of the type. This is in contrast to when using a type synonym which does not require any use of a constructor. Now what happens when we try to create an invalid date like we did before? Well, in that case, the code does not even compile. We get told where the expected type is day, we have given a month, and where the expected type is month, we have given a day. You can see why using a Newtype declaration is more type safe than using simple synonyms. The Newtype declaration is very similar to the declaration for type synonyms, so let's make it clear what exactly the difference is. Unlike a type synonym, which is actually just a synonym for an existing type, like I said before, a new type will be treated like a completely separate type than the thing it wraps. A restriction which you should know about when it comes to Newtype declarations is that they can only have a single constructor with exactly one field in it. We will cover constructors in more depth later on when we look at union types, which do not have this restriction and so can have multiple constructors. Since the Newtype declaration will only ever contain a single constructor with a single field, you can see why it's also known as a datatype renaming. For example, in our case, the day, month and year types are kind of just datatype renamings for an int. For additional information, check out section 4.2.3 in the Haskell 2010 report and the article on Newtype declarations on the Haskell wiki. Some of the concepts we discussed here, like constructors, will be covered in much more depth later on in the module, so don't worry if you don't understand them fully right now. I've just shown you how to make Newtype declarations so that you are aware of them. It is not important to necessarily use them for a beginner. We are going to take an aside here for a few minutes whilst I try to explain one of the problems a beginner might face whilst being introduced to Haskell. We previously defined 3 new types: day, month and year. Now let's say we want to explore this in GHCI, so we load our code and everything compiles and looks good. But if we try to see the value of D1 in GHCI, unfortunately we see an error. The error states that there is no instance for show day. What exactly does that mean? Well, unfortunately, we are not at a point where we can actually understand this error completely. To understand why this happens, we need to have covered the topic of type classes. Now we will cover type classes later in the course, in a future module, and so we are kind of in a chicken and egg situation here. To fully understand this, we need to know about type classes, but to fully understand type classes, we need to know about types, the focus of this module. We want to be able to have access to GHCI so we can play around with our code interactively. So for now, I'm going to ask you to take a leap of faith and add the code deriving show to the end of the type declarations and reload your GHCI session. And now when you try to see your values in GHCI, they appear as you would expect. Although currently we cannot understand what the deriving show is doing completely, I can try to give you a partial explanation. For each of the types, day, month and year, it is instructing the compiler to generate some default code for, in this case, the show type class. This generated code is what allows us to have the value converted into a string and printed on the screen in GHCI. Don't worry about this too much. Just add it to the end of your type declarations when you want this functionality. We will cover type classes in the future, and you will understand this fully then. Let's now discuss how we can create what is known as a product type with some example code. There is some new syntax here and some slightly weird naming, which I will explain. The data keyword indicates that we are creating our own custom type. Then comes the name of the type, which in this case I've called datetc. Then comes an equal sign. After the equal sign comes what is known as a data constructor, and then the types of components we want for the product type, which in this case are 3 ints. Each component is simply separated by a space. We are using ints here to represent the constituent parts of the date, those being the day, month and year. We use ints for simplicity and will come back to better alternatives later. So we can read this code like this. We are creating a custom type called datetc, which is defined as having a single data constructor, datedc, which expects 3 ints. We also add the deriving show clause to the end of our data declaration so that we are able to print values of our newly created type on the screen in GHCI. Now, a quick word about constructors. The datetc, which you see here, which is to the left of the equal sign, is sometimes called the type constructor, hence the reason for me putting a tc in the name. We will learn more about parameters to the type constructor later when we look at polymorphic types, but in this particular case there are no parameters to the constructor, so we can just refer to datetc as the type name. The type name is what you would use in signatures to refer to the type. The datedc, which is what you see here, is to the right of the equal sign and is known as a data constructor, hence the reason for me putting a dc in the name. Sometimes people call it a value constructor instead, but they both mean the same thing. We use this constructor to create values which have the type datetc. This constructor takes 3 int arguments. Let's take a second to understand what this all means by looking at how we can create instances of our new custom type. Here we are creating 2 values, d2 and d3, which both have the same type, datetc. We refer to the type constructor's name in the type signature. And when we want to create an instance of the value, we refer to the data constructor. Remember, Another name for the data constructor is the value constructor for this very reason. They are called product types because they're analogous to the Cartesian product of sets which we saw before. In other words, a value of the datetc type can contain any combination of 3 ints, just like a 3-tuple of int would be able to. But unlike a 3-tuple of ints, we have a much stronger type safety available here when we use our custom type, and our code will be more readable as well, since all type signatures will now refer to our custom type name, which is somewhat self-describing. One thing I should mention is to do with naming. As you can see, the type constructor and the data constructor always begin with a capital letter. Also, the TC and DC at the end of the constructor names in the type declaration are not actually needed. I only put them there to get you familiar with the idea of the type constructor and data constructor being 2 separate things. In actual fact, the typical declaration you would see in Haskell is more like this, and we would create instances of the type like so. And so, the date in the type signature here refers to the type constructor, and the date in the values refers to the data constructor. In Haskell, the names of the types and values are independent of each other, and so there is no actual name clash occurring. You just need to keep the namespace for the type constructor names and value constructor names separate in your head. This can be quite confusing at first, but after a while, you get used to it. It should be clear now why we are calling them constructors, because they are defined with parameters, and when arguments are given to them, they construct an instance. In the case of this particular type constructor, it does not actually take any parameters. As I mentioned earlier, we'll be looking at type constructors which take parameters when we look at polymorphic types later. So let's just focus on the data constructor for now. The data constructor acts exactly like a function would. If we ask GHCI for the type of the data constructor datetc, it responds by telling us that it takes 3 ints and returns a datetc. And you can see, when we use the data constructor, it is just like calling a function. Remember, :t in GHCI is short for :type, so when we use the :t command, we are asking for the type of a value or a function. So when we ask for the type of the date, like we do here, we get the response that it is a function which takes 3 ints and returns a date. But what date exactly? Is it the date we define here for the type constructor, or the date we define here as the data constructor? Well, the first date refers to the data constructor. This is the date which we are asking GHCI to tell us the type for, and the second date refers to the type constructor. If you get confused, then remember that the only thing that can appear in a type signature, that is, after the double colon, is a type, and so the date within the type signature refers to the type, not the value. If you are still confused, you can compare it with the type signature given for datetc here to understand which is the type and which is the data constructor. Now what happens when we ask for the type of the type constructor itself? As you can see here, we get an error. That's because you can only use :t to ask for the type of values or functions, not for asking for the type of a type, so the error is expected. We'll look at the type of types later when we cover polymorphic types. One of the definitely good things that happen when we have our own types like this is that in type signatures, our intent becomes much more clearer. By reading this type signature, you know for sure that the values are intended to be dates. This is much better than using a simple 3-tuple to represent the constituent parts. In this particular type signature, you have no clue that the 3 ints are supposed to represent a date. So using our own custom types to make things clearer and more understandable makes a lot of sense. But still, the usage of raw ints here is still error-prone because they do not constrain the possible values to be only valid values. We could still construct an invalid instance of a date, like here, where we are saying that the month field has a value of 31, when obviously there is no 31st month. So we still need to learn more about types before we can fix this. But that's pretty much it for creating your own product types. It's quite simple really. You use the data keyword followed by the name of the type and an equal sign, followed by a constructor and the types of the constituent parts. And although we don't always need to, we add the deriving show clause to the end of the type declaration for convenience, so that we can see the values in GHCI, like we did here. In addition to product types, which we have already seen, there are also sum types in Haskell. We'll see why it's called a sum type in a bit. Sum types are sometimes alternatively referred to as a union type because of how they are similar to unions in set theory. Technically, Haskell has what is known as tagged union types. but as a beginner, the distinction between tagged and untagged unions is not too important, and so we will use the terms SumType and UnionType interchangeably. We have already seen how we can use the Bool type in Haskell. We can declare variables to have the type Bool, and then we give our variables either a true or false value. You can't have a half true or half false value. Values can only ever be true or false. Let's see how the Bool type is actually defined in Haskell. The Bool type is defined like so. We've already seen similar type declarations for product types, but this one is slightly different, so let's describe it from scratch. The data keyword indicates that we are creating a type. Then comes the name of the type, which in this case is Bool. Then comes an equal sign. After the equal sign comes two constructors, separated by a pipe symbol in the middle. We read the pipe as OR, so we read this as true or false. So the whole definition can be read as, we are defining a data type called Bool, which has the constructors true or false. Remember, the name of the type and all of the constructors should always begin with a capital letter. The key piece of syntax when defining some types is the pipe symbol, which is placed between each of the possible values, which we have seen means OR, so true or false. Bool is an example of a sum type in Haskell because the number of possible values of the type is defined by the sum of the number of constructors. In this case there are two constructors, true and false, so the sum of possible values is 2. Bool is probably the simplest sum type that you can come across because there are only two possible values and the constructors themselves do not take any arguments. We will see some more complicated sum types later. Here is a quick exercise for you. Pause for a few seconds and try to define your own type called month, which lists all of the months in the year, and then define some instances of the type. If you need to, check out the definition of Bool, which we saw before, to refresh your memory on how to define a custom sum type. Okay, let's see how we would do that. Here is the data type definition, and here are some instances of the type month, which we have defined. Let's focus on the data type definition. We are creating a custom type called month, which can take the values January or February or March and so on. We add the deriving show clause to our type declaration so that when we try to view instances of the month type in GHCI, they will be displayed without running into any annoying errors. Now, when it comes to creating values of the type, we declare them to have the type month, and then we call the constructor we want. So for Jan, we are calling the January constructor, and for Feb, the February constructor, and so on. These constructors, in this case, do not take any arguments. And if we ask for the values in GHCI, since we added the deriving show clause to our type declaration, the values are shown just fine. The sum types we have seen so far, Bool and month, have been very simple. Their constructors take no arguments, and so are known as nullary constructors. Some people refer to data types like these as enumeration types. This is because they simply enumerate over all possible values in a fixed set. So if we want to represent a month somehow, then creating an enumeration type like this makes absolute sense. It is a much superior way than using a type such as an int, whose possible values are much more than the fixed number of months in a year. Let's now look at some contrived examples to further our understanding of sum and product types. In this example, we are creating a type called status, which is supposed to represent whether something succeeded or failed. Status is a sum type, since it can be either a success or a failure. We define a success using a nullary constructor, i.e. a constructor which does not have any arguments, and a failure with a constructor which takes an int8 argument. The idea here is that if there is a failure, we provide a failure code, which is an int8. Now int8 is a special version of int which only has 8 bits of precision. We need to import the type to use it, and hence the need for the import statement at the top. Since there are only 8 bits of precision, an int8 value can be any of the 256 integers between -128 to +127 inclusive. Here is an exercise for you. Try to figure out the number of possible values a status can take. How would we actually go about calculating that? Okay, well, status is a sum type, so all we need to do is sum the number of different values the underlying types can take. The first value we know, it can take the simple value of success. Success is a nullary constructor, so it only counts as one value. Then we know it can take a failure. A failure constructor contains an int8 value with it, and we know that the int8 could be any one of 256 integers, so we just need to sum the two, the one from the success and the 256 from the failure, to give us 257. So the status type has 257 possible values. Let's have a look at another contrived example. Here is a data type which we are defining called A, which can be either an A, B or C. Since there are multiple constructors, we know A is a sum type, and since two of the constructors A and B take parameters, we also know it is a product type. So, now the same exercise for this new type. How many possible values can A take? This one is slightly more difficult than the previous one, so I'll pause for a few seconds. Let's start figuring this out by looking at the first constructor, which is A. Since A takes more than one type as a parameter, we know it is a product. For Bool, it can take two values, either true or false. For an int8, we know it can take one of 256 values. So for the product type, to get the total number of values, we need to find the product. Simple really, it's in the name. To find the product, we just multiply 2 times 256. It's 512. So if you have a value with the A constructor, it can be any of 512 values. Now for the second constructor, which is B. This is a product type too, and the number of values which it can take is equal to 256 multiplied by 256 multiplied by 256 multiplied by 2, which is roughly equal to 33.5 million. All we are doing is multiplying each of the possible values each individual type can take. Now for the final constructor, C. It is a null array constructor, so it can only take one value. That is the value of the constructor itself. And so to get the total number of values which a value of type A could possibly be, we sum up for each of the branches in the union. That's 512 plus 33,554,432 plus 1. So you can see why they are called sum and product types. To find out the possible number of values, you either have to find the product or sum them, or in this case, both. Algebraic data types are types which are formed by combining other types. They are a collection of data constructors. They are called algebraic data types because they form an algebra of types with two primitive operations which we have seen, the product and the sum. We saw this in action in the previous slide, where we were able to use the algebra to calculate the total number of possible values a type has. Quoting from the Scala glossary, we have an alternative definition, which you may find more useful. An algebraic data type is a type defined by providing several alternatives, each of which comes with its own constructor. In the general sense, in Haskell, an algebraic data type will follow the template shown in this code block. We have multiple constructors, and each constructor takes a list of types as parameters separated by a space. The list, of course, could be empty, as is the case for constructor 4. As you have seen, we can combine sums and products to create quite complicated types, but Haskell gives us a nice and simple syntax to define them. The lightweight syntax Haskell provides to define new data types incentivizes us to create a rich model using algebraic data types for our programs. This in turn makes our programs more strongly typed and readable. We've covered a lot in this module. We began by looking at the theory and understanding that tuples are inbuilt product types in Haskell, but they are limited because they do not provide the level of type safety we want in our programs. We also looked at type synonyms and data type renamings and understood their limitations, with type synonyms only really providing slight readability benefits and renamings being limited to only having a single constructor in the definition. We then took a slight stop where we explained that you can add the deriving show clause to your data type definitions to get them to print on the screen in GHCI. But we also acknowledged that to fully understand how things worked, we would need to wait until we covered type classes in a later module. We moved on to creating our own custom product and sum types, culminating in us finally understanding what algebraic data types are, a combination of sum and product types in one. By learning about the algebra of sum and product types and seeing them in practice, you are now well equipped to create your own custom algebraic data types in your programs. The next modules in the course will build on your knowledge further by covering other essential concepts such as pattern matching, polymorphism, and of course type classes. See you there!